Chapter 16, Electrochemistry. I'm going to try to put all of the learning objectives at the first of each of the chapters. And so for this one, things y'all ought to know before we finish. And by the time we finish the chapter, y'all ought to know all of the terms that are either in bold or in italics in the chapters. You ought to recognize vocabulary words, but we ought to know things like oxidizing agent, reducing agent, oxidation, reduction, what's the cathode, what's the anode. By the end of this, we should be able to balance half reactions and balance redox reactions using the half reaction method in both acidic and basic solutions. Y'all ought to be able to sketch a voltaic cell, which is really a battery, and give the half reactions for each of the different compartments. And then draw like diagrams for the direction for the electrons flow, how do the ions flow inside each of the cells. We're eventually going to be able to calculate the EMF for both standard cells and for as well as cells under real conditions, given the Nernst equation. And then we also should be able to recognize that the reduction potentials that we see in books, the standard reduction potential E0, are relative to that of the standard hydrogen electrode, which is defined as a potential of 0. You should be able to use the EMF, which is really the voltage for a battery, and the delta G to predict spontaneity, where delta G is equal to negative NFE. Again, when is it spontaneous for delta G? Delta G for a spontaneous reaction has a negative delta G. The voltage has to be positive for a spontaneous reaction. Y'all ought to be able, by the time we're done with this, you should be able to explain how and why a concentration cell works. Even though they've got the same anode and cathode, but they have different concentrations of ions in each solution. You ought to be able to understand why do things rust or tarnish if it's not iron. And for that matter, how does an alkaline battery work? How do fuel cells work? For that matter, what in the world is a fuel cell? And how does a lead-acid battery work? We ought to be able to understand what corrosion is and how do we prevent it from occurring or at least slow it down. We're also going to discuss and describe electrolytic cells, and y'all should be able to understand the difference between an electrolytic cell and a galvanic cell. And then we should also be able to do some calculations related to electrolysis. For electrochemical reactions, electrons are transferred from one species to another. And these can be in the gas phase, these could be in solution, or these could be in solids. In order to keep track of what loses electrons and what gains the electrons, we need to assign oxidation numbers. Things to remember, anything in their elemental states has an oxidation state of 0. Typically, it's species with a charge on them. Their charge is their oxidation state. So in this case, I've got H plus that has a +1 oxidation state. Zinc 2 plus has a 2 plus oxidation state. So in our reaction, I've got elemental zinc with an oxidation state of 0 reacts with H plus with an oxidation state of +1 to give me zinc +2, and then generate hydrogen gas, and since it's elemental hydrogen, it has an oxidation state of 0. Some vocabulary words. A species is oxidized when it loses electrons. So in our case, zinc 0, zinc elemental, loses 2 electrons to form zinc 2 plus. We would say that the zinc metal is oxidized and it loses 2 electrons. A species is reduced when it gains electrons. So in this case, we've got hydrogen +1 gains an electron to give us hydrogen 0. So the hydrogen is reduced to give elemental hydrogen. The mnemonic that goes with this is oil rig. Oxidation is loss, reduction is gain, where that's oxidation is loss of electrons and reduction is gain of electrons. So in our case, the zinc is oxidized and the hydrogen is reduced. All right, more vocabulary words. What is reduced is the oxidizing agent. Hydrogen is the oxidizing agent because, and as hydrogen is reduced, hydrogen oxidizes zinc metal by taking electrons from it. Now, what is oxidized is the reducing agent. Zinc is oxidized, but it reduces hydrogen by giving its 2 electrons to the hydrogen to make hydrogen gas. One of the things that you all will be able to do when we finish this chapter is that you'll all be able to balance redox reactions. We introduced redox reactions in chapter 4, but didn't really give you the tools to be able to do it. And in this chapter, we'll actually systematically walk through and teach you how to balance redox reactions using the half reaction method. In the half reaction method, we separate the redox reaction into an oxidation and reduction half reactions. We balance the electrons that get transferred, and then we balance all of the other atoms that are in the reaction. So for example, in the reaction of H2S plus iron 3 plus goes to yield sulfur, elemental sulfur, iron 2 plus, and H plus. Now, how do I know it's a redox reaction? Some signs are that I get different oxidation states of the iron on the different sides, and I also have elemental sulfur on one side and distinctly not elemental sulfur on the other side. Now, so to do this, I'm going to need to, so I break it into my reduction reaction. So I've got iron 3 plus gives up gains an electron to give me iron 2 plus. That's the reduction. The oxidation is that H2S goes to form elemental sulfur plus 2 H pluses and gives up 2 electrons. I can't just balance this reaction, or it's balanced with elements, but it doesn't balance with electrons. And so I have to multiply the top reaction by 2 so that I lose 2 electrons and I gain 2 electrons. Now at which point I can simply add the reactions together. My electrons cancel out, I gain 2 electrons, I lose 2 electrons, and I end up with the equation at the bottom, which is now balanced, and it's also balanced with equal numbers of electrons being transferred. Redox reactions will often say that they need to be balanced in either an acidic solution or a basic solution, or an acidic or basic media. So here's a reaction that says it needs to be balanced in an acidic media. I've got iron 2 plus reacts with Cr2O7 2 minus to give me iron 3 plus and chromium 3 plus. How do I know it's a redox reaction? I've got 2 different oxidation states of iron in my reaction. So how do I start? So we got to keep track of our electrons. So my iron 2 plus goes to form iron 3 plus. Does it gain or lose electrons? It goes from 2 plus to 3 plus. It loses 1 electron. So I'm going to lose 1 electron. Now, for my chromium, I've got chromium that's going to form chromium 3 plus, but I need to know what's the oxidation state of chromium. So this is one where things I know that oxygen is in a compound is almost always -2, so I can think about having 2 times some oxidation state for the chromium plus 7 times -2 for the oxygen, and all of that has to add up to a -2 overall charge on the molecule. So my oxygens are equal to a -14, -2, and then my chromium what -14 is -2, this has to be 12, 2 times a +6, would be equivalent to my chromiums being at a +6 oxidation state. So my chromium goes from +6 to +3. Each chromium gains 3 electrons, right? So 3 electrons for each chromium. Now, but I've got 2 chromiums on the left, and so I've got to have 2 chromiums on the right, and each chromium is going to gain 3 electrons, so I'm going to multiply this by 2 as well. So this gives me I have to gain a total of 6 electrons. For a redox reaction, I have to gain and lose the same number of electrons. So I'm gaining 6 electrons, so I have to lose 6 electrons as well. So each iron loses 1 electron, so that means I'm going to have to multiply this by 6 so that I now lose a total of 6 electrons. So then I'm going to have to have 6 irons on that side, 6 irons on that side. So each iron is losing 1 electron, so I've got to have 6 irons to lose 6 electrons. Is my equation balanced? Almost. I'm missing oxygens. I've got oxygens on the left side. I do not have oxygens on the right side. How do I get the oxygens? I typically will add them by adding waters to the side needing oxygens. So the right side needs 7 oxygens, so I will add 7 waters to the right side. Okay, is it balanced now? Oh, no. Now I got my oxygens, but now my protons are off because I've got 7 oxygens, but I've got 14 hydrogens on the right side, but I've got none on the other side. So how will I get those back? I will simply add 14 H pluses, and that will balance our equation. Why do I do that? It says it's in acidic media, and so this way I now have 14 H pluses. It's certainly acidic. So on this side I've got my 14 hydrogens. I've got 14 hydrogens on this side. I've got 6 irons. I've got 6 irons. I've got 2 chromiums. I've got 2 chromiums. I've got 7 oxygens. I've got 7 oxygens. So my equation is balanced. I have also added some slides that will systematically walk you through the balancing of the equation as well. So again, here's our unbalanced equation. We're going to separate them out into the oxidation half reaction, and the reduction half reaction. I'm going to need to balance all of the other atoms other than oxygen and hydrogen. So again, I've got to add my 2 chromiums. I can now go ahead and balance my oxygens and hydrogens by adding water and H pluses. And then I'm going to add my electrons so that I make sure that I account for the oxidation and the reduction of each of my individual atoms in solution. Once I've added the electrons, I'm going to have to multiply my iron by 6, much like we did last time, so that I'm going to lose 6 electrons. I gain 6 electrons with the chromium. I can now add the 2 reactions together, and I get exactly the same equation that we just solved doing it the other method. Again, there are lots of different methods for doing this. And then we can go back and so what's the left down below? Basically, we've now gone through and verified that we've got all of the irons and chromiums and hydrogens and oxygens, that they're equal on both sides, and that my charges are equal too. Some reactions need to be balanced in basic media or basic solutions. So here's an example of one of those. But we're going to do it exactly the same way as we did the one in an acidic solution. So essentially, you guys learn one technique for doing this, and it applies to both acidic and basic media. The only difference is that once it's balanced in acidic media, we're then going to add hydroxides to neutralize all of the excess H pluses that are there, so that it's now in a basic solution. So, looking at this equation, is it a redox equation? Absolutely, right? I've got an I minus on one side in one oxidation state. I've got an I2 on the other. All right, so my I2 is elemental iodine, so it's in an oxidation state of 0. My I minus is an oxidation state of -1. All right, so in this case, my iodine goes from I minus to I0. So each iodine is losing one electron, minus one electron. But I have two of them because since I'm making I2, so I've got to multiply this by 2. So then I'm actually losing 2 electrons. Okay, now the manganese. Manganese MnO4 minus on one side, manganese O2 on the other side. Again, oxygen almost always minus 2, so that means my manganese has to be plus 4. On that side, and on this side, again, we can do the same way. What's a manganese oxidation state? If it's not obvious, I can go, oh, it's something. But then again, I got plus my oxygens, and each of them is minus 2, so I got 4 oxygens times a minus 2 has to add up to a minus 1. So that means blank plus 8 has to equal minus 1, right? And therefore, my manganese has to be at a plus 7. So my manganese in permanganate is at a plus 7 oxidation state. All right, so manganese goes from plus 7 to plus 4. It gains 3 electrons. So it gains 3 electrons, and I've only got one of those. So it gains 3 electrons. All right, so again, now I've got to, but I can't gain more electrons than I lose. I'm losing 2 electrons, but I'm gaining 3. So I need to find a common denominator between those. So really it's like fractions, right? So the common denominator between 2 and 3 is 6. So why don't we multiply this one by 2 so that I'm now going to gain 6 electrons. So then I have to multiply this by 2, multiply both of my manganeses by 2, and then I have to multiply this one by 3 so that I now lose 6 electrons for my iodine. Then I multiply my iodines by 3 as well. So this becomes 6, and then this becomes 3 over here. Am I balanced? No. Now that I've now balanced my electrons, and I've balanced my manganese, and I've balanced my iodines. The only thing I have left to balance, ideally, would be just my oxygens. On the left side, I've got 4 times 2, I've got 8 oxygens here. On the right side, I've got 4 oxygens here, so I need to add 4 more oxygens. I'll add them by adding them in the form of water. So I'll add 4 H2Os onto that side. I'm still not balanced because now I've added hydrogens, and so now I've got 8 hydrogens over there. I've got to get 8 hydrogens on this side. How will I balance those? Just like last time, I will add 8 pluses. And now I'm balanced, and honestly, the equation is correctly balanced in an acidic solution. The downside of it is it wants me to balance it in a basic solution. So how do I balance out? How do I get rid of my 8 protons? Well, I'm going to add 8 hydroxides to those to neutralize them, and it's like a mathematical equation, and what I do to one side I have to do to the other. So I'm going to add 8 OHs to this side, and I'm also going to add 8 OHs to this side. Now, what do 8 protons and 8 hydroxides make? They make 8 waters. Now, technically, my equation is balanced, but I can clean it up by canceling out my waters. On the right side, I've got 4 waters. On the left side, I've got 8 waters. And so if I subtract off the waters, I get rid of those, and I can convert these to 4 waters. I would now have a balanced equation. So let me rewrite this. Okay, so I've now rewritten the equation. So I've got 4 waters on this side in place of the 8 waters. And so now if I go back and look at it, here I would have, I've got my 8 hydrogens here, I've got 8 OHs, 8 hydrogens there, I've got 4 oxygens here and another 8 oxygens here. That should give me the same number of oxygens on this side that I've got over here, where I've got 4 oxygens here and 8 oxygens over there. 2 manganese, 2 manganese, 6 iodines, 6 iodines. My equation is balanced, and it's in a balanced, and it's in a basic solution. How do I know it's basic? Because I've got excess hydroxides present. In the PowerPoint, I've also included that systematic approach as well, where again, here we'll start off with our equation. Here's my unbalanced equation. We can separate it into half reactions: oxidation reaction, reduction reaction. We can again balance everything other than oxygens or hydrogens, which means I've got to balance my iodines there. We can now go back in and balance all of our oxygens and hydrogens in individual half reactions. Now going back in and adding my electrons to make sure that I balance each of my electrons out so I know how many electrons I gain and lose. Multiplying each of those half reactions by the appropriate constant so that I lose and gain the same number of electrons. So again, I've got 6 electrons here that I'm losing. I'm gaining 6 electrons here. Summing the two equations together, I get exactly the same equation I've got, except again, it's now in an acidic solution. Again, add hydroxides to both sides and then cancel out all of my excess waters, and I get exactly the same equation we had before. It really is a beautiful system.